I'm almost sorry to say that today we're going to talk about particle physics. Almost sorry, but not really.
And hey, I'm back, so that's something, right?
It is. And we also have stories on gravitational waves and the latest, most distant discovered galaxy.
Always breaking records. Eric will be joining us to talk about the Axiom 1 launch.
And another update on the JWST.
Plus, at the end of the show, I interview Dr. Kelsi Singer from the Southwest Research Institute about cryovolcanoes on Pluto.
All that and more, right here on the Daily Space. I'm your host, Dr. Pamela Gay.
And I'm your host, Beth Johnson.
And we're here to put science in your brain.
A while ago, we provided an update on the optical alignment of the different instruments of the JWST to its telescope, with the exception of one, the mid-infrared instrument, or MIRI, because of the cold temperature needed. Here is more information on how exactly it will get down to its 7 Kelvin operating temperature. Cold helium gas has been flowing over the instrument, but that's only enough to get it down to 15 Kelvin. To finish cooling, MIRI has its own cryocooler, which takes the helium gas and squeezes it. The gas cools as it expands out of the cooler, cooling the MIRI instrument with it. This cooling is necessary to see exoplanets with temperatures thought to be similar to Earth. MIRI has 4 coronagraphs to precisely separate these planets from their host stars and characterize their atmosphere's chemical makeup. And now, for a launch. Eric?
A SpaceX Falcon 9 launched Crew Dragon Endeavour towards its third docking to the International Space Station on April 8th at 1517 UTC, carrying 4 commercial astronauts conducting Axiom Space's AX-1 mission. It has goals of getting experience in microgravity and also conducting research and philanthropic activities. Let's watch the launch. Also making another trip sending people into orbit was Falcon 9 First Stage 1062, making its 5th flight. It successfully landed on the drone ship A Shortfall of Gravitas. Over the last few years, NASA has been trying to encourage the commercial use of space, and in particular of the ISS. Besides the commercial facilities, and even an airlock module, there have been 2 programs to provide services to the ISS. The Commercial Cargo Program and Commercial Crew Program. Commercial Cargo essentially saved SpaceX from bankruptcy after 3 failed Falcon 1 launches in the early days of the company. The next major part was the Commercial Crew Program, under which NASA contracted 2 companies, SpaceX and Boeing, to design and build spacecraft to take NASA astronauts and others to orbit. The end result of this was SpaceX's Crew Dragon, developed with NASA funding and technical support. Boeing is still trying. This mission, the next phase of NASA's efforts to encourage the commercial use of space, is the first wholly commercial-operated crewed mission to the ISS. NASA has contracted with Axiom to attach modules to the ISS US segment over the years leading up to the deorbiting of the ISS. Prior to it being deorbited, currently scheduled for 2028, The Axiom modules will become their own independent space station. This first module is scheduled to go up to the ISS in 2024. After 22 hours in orbit facing towards the ISS, a long time compared to the 3 to 6 hours of the Soyuz that NASA astronauts in previous space shorts used to fly on, the capsule autonomously docked to the zenith, or space-facing port, of Node 2 on April 9th. Crew Dragon takes this slower approach because it's easier on mission planning and there is much more space in the Crew Dragon than in the Soyuz module. They will spend 8 days docked to the ISS, doing science and philanthropic activities. Following their first flight, Axiom plans to offer crewed flights to the ISS as often as twice per year, quote, aligning with the flight opportunities as they are made available by NASA, end quote. The crew of AX-1 is composed of former NASA astronaut and current Director of Business Development at Axiom Space, Michael Lopez Alegria, and 3 private astronauts, Larry Connor, A10 Stibbe, and Mark Pathy. Lopez Alegria flew to space 4 previous times, 3 times on the Space Shuttle and once on a Soyuz. This flight makes him only the 7th person to fly into space on 3 different types of spacecraft, after Walter Schirra, John Young, Shane Kimbrough, Aki Hoshida, Soichi Noguchi, and Thomas Marshburn. He was commander of Expedition 14 in 2006 and set several space records, including the second most EVA time overall over the course of 10 EVAs. The AX-1 crew will conduct a packed program of science, with the crew performing more than 25 experiments in many areas. These include stem cell studies for cancer research and, quote, self-assembling satellites, among others. MIT's Tesserae experiment is exploring self-assembling satellites. This experiment consists of a series of tiles with magnets, which once on the ISS, will unfold and assemble themselves into a structure autonomously. These structures will have many uses in the future, including a future space telescope's mirror and a base on the surface of another planetary body. The cancer stem cell experiment will use microgravity to age cancer stem cells faster than they would on Earth. It will evaluate the early stages of cancer in structures called tumor organoids, which are artificially constructed models of small parts of the human body produced to study specific things. The experiment, which will look for certain molecules called biomarkers, which can help provide an early diagnosis of cancer. On orbit, the crew will examine the samples in a microscope as they go through cycles of growth. We'll have updates on all of these experiments and more when AX-1 returns to Earth, and we'll bring you coverage of SpaceX's Crew 4 mission that is scheduled to launch later this month. We'll have updates on all of these experiments and more when AX-1 returns to Earth on April 18th. And we'll also bring you coverage of SpaceX's Crew 4 mission that is scheduled to launch later this month. Coming up next, we have some astronomy, particle physics, and planetary science news. Stay tuned.
Last week we brought you news of Arendelle, the newest, furthest star. Its light traveled 12.9 billion years to reach us, and that is overwhelmingly far for a universe that is only 13.8 billion years old. But Arendelle is just one star, and galaxies, with their diversity of stars and bright gas, can be seen to even greater distances. And today, we have a new farthest galaxy to present. Like Arendelle, this object's light was enhanced by a galaxy cluster acting as a gravitational lens. Catalogued as HD1, this smudge of light was discovered in 1,200 hours of data taken by the combo of the Subaru Telescope, Vista Telescope, UK Infrared Telescope, and Spitzer Space Telescope. It was then confirmed with the Atacama Large Millimeter Array. Or at least confirmed as well as anything this faint and far can be confirmed. According to ALMA observer Akio Onawe, we found a weak signal at the frequency where an oxygen emission line was expected, The significance of the signal is 99.99%. If this signal is real, this is evidence that HD1 exists 13.5 billion light years away. But we cannot be sure without a significance of 99.999% or more. This work is published in the Astrophysical Journal with the lead author Yuichi Hurricane. Formed when the universe was just 300 million years old, this galaxy is remarkably bright. It is either undergoing massive star formation or has an active black hole, or both. When? Is it too soon to say when? When JWST starts doing science, HD1 is selected to be studied during JWST's Cycle 1 observations.
When you hear about the farthest, youngest, or otherwise early in the universe object being discovered, exactly how it is described can be confusing. As the light from distant objects like HD1 has traveled toward us, space has been expanding, and the distance between us and the object the light has to travel from has been changing. I like to say how long the light traveled. That doesn't tell you where the object is, but it reminds you that we're seeing it as it was, not as it is. Distance is also a bit nonsensical. We know how far the light traveled, 13.5 billion light years, but that distance isn't the same as the distance between us and that object today, or us and the object when it formed. It's more like trying to say how far someone had to run when they ran up the down escalator. They might have ended up traveling one story, but they had to run up more than just one story worth of stairs, and it is all a bit messy to sort. And making it more complicated, time is not constant, and space can change too. Gravitational waves are the space-time equivalent of crash alarms. When massive objects orbit closely, they radiate energy in the form of gravitational waves. Like sound waves, these waves compress and expand what's around them. But while sound waves change air, gravitational waves compress and expand space itself. We can detect the waves from merging black holes and neutron stars with detectors here on Earth. But just like there are sounds ears can't hear, there are gravitational waves both too long and too short for us to detect with the size of detectors we can put on our planet. Researchers want to detect all sizes of crashes, though, so they get creative. Researchers started using pulsars to look for massive waves a while back. With radio telescopes, they looked for slight changes in pulsar timing that would indicate space expansions and contractions between us and the pulsars. And this is awesome! Except a lot of random things between us and pulsars can interact with radio light, including things like random electrons. To escape this issue, researchers have started monitoring pulsars in gamma ray light, a high energy color that pretty much just flies straight and true without interruption. After 5 years of data, researcher and co-lead of this study, Aditya Parthasathari, says the Fermi results are already 30% as good as the radio pulsar timing arrays when it comes to potentially detecting the gravitational wave background. With another 5 years of pulsar data collection and analysis, it'll be equally capable with the added bonus of not having to worry about all those stray electrons. While nothing has been seen yet, the kinds of supermassive black hole mergers this may detect are rare, and the quality isn't yet the best. But it will get there, and someday we may see gravitational waves in the changing shape of space using Fermi. This work appears in the journal Science and comes from the Fermi LAT collaboration.
Before switching to more down-to-earth science, we want to call your attention to the possible detection of a particle, the W boson, in data from the Chicago area Fermi National Accelerator Lab's Tevatron Collider. Now turned off, the experiment ran until 2011, and its wealth of data is still being searched for the signatures of particles popping in and out of existence. The W boson is part of the weak force and is involved in a variety of decay processes. Measuring the masses of bosons like the W boson and its more famous cousin, the Higgs boson, is key to testing our current understanding of particle physics. And while the Higgs boson is everything we ever expected, the data from Fermi hint at the W boson being statistically much heavier than previously thought. If this is true, it opens the door for new physics and requires rethinking old ideas. The results being looked at only come from one facility. At Fermi, protons and antiprotons accelerated into one another and produced cascades of particles out of the energy. And researchers had to piece together all those tracks so they could say these resulting particles all came from the decay of this one unstable thing that had this one mass. This is not easy. And while the data looks good, that doesn't mean it is certain. We look forward to other accelerators repeating the experiment. And for now, we remain open to both the possibility that everything is as it should be with the universe and Fermilab was wrong, and to the possibility that we were wrong and everything needs to be rethought because Fermilab is right.
Sometimes getting things right is a matter of getting a fresh perspective. In the case of volcanoes, scientists have brought drones to the summit of Mount Merapi in Indonesia in order to get a better look at a new lava dome. The dome has been forming since 2018, but had begun collapsing, and the scientists wanted to find out just how and why it was collapsing. This volcano is Indonesia's most active one, which means understanding it is very important to the health and well-being of the local population. Using drones, the team captured over 1,000 high-resolution images from about 500 meters above the lava dome. They'd already been using this method, and with the additional time, they were able to see what was going on with this newer dome. Mind you, it's not easy to get usable images at the top of an active volcano. As co-author Valentin Troll explains, gas emissions or clouds can obscure the view into the crater and onto the dome at times. From an entire decade's worth of data, researchers discovered that there was a horseshoe-shaped fracture system that had formed in 2012 and was buried by lava in 2018. That fracture zone weakened the new dome, which then collapsed in 2019. Additionally, the fracture system is allowing hydrothermal alteration of the minerals in the rocks to occur, which is further weakening the rock. Their results were published in the journal Scientific Reports. And now they know what to keep an eye on in the future from drones in the sky. Speaking of volcanoes, how about some cryovolcanoes? Stay tuned. As we reported a couple of weeks ago, a new analysis of images taken by the New Horizons spacecraft as it flew by Pluto has found several giant ice volcanoes that seem to have been active in the geologically recent past. These findings suggest that Pluto managed to hang on to its internal heat longer than previously thought, and that could change our perspective on other bodies in our solar system. The results were published in Nature Communications and led by Dr. Kelsi Singer. And now we are pleased to be joined by Dr. Singer, who is a senior research scientist at the Southwest Research Institute. Additionally, she is a New Horizons co-investigator and deputy project scientist, having worked on the mission since her postdoc position back in 2014. Thank you for joining us, Dr. Singer, and welcome.
Thank you for having me, Beth. Good to talk to you.
Good to talk to you, too. I mean, we've sort of talked on Twitter, but that's been about it. So tell me about this research. How did you, where did this discovery come from? What images were you looking at? What were you looking for? Was this a happenstance kind of thing, or were you looking for this?
Great question. Well, it's interesting because some of the very first pictures that we got back after the New Horizons flyby of Pluto in 2015, we actually weren't able to send back all the pictures right away because we have relatively low data rates because we're so far away. But we sent back kind of like little postage stamp areas on Pluto so we could get kind of a sampling. And it just so happens that this area was in one of those postage stamps. And it is a really strange area. You showed the picture of it, and it doesn't look like anywhere else in the solar system.
Mm-hmm.
So in a way, we kind of noticed that it was different and interesting right away. But it took us a long time to get the rest of the data back. And that's basically what we did here, was say, okay, we know this is weird, but what is it? And so we spent a lot of time analyzing all the images, all the other kinds of data we have, like composition data. And that's how we started to really dig into this region.
So tell us about this region. What did you discover here?
Well, what we think we've found is a number, 10, possibly even more, it's hard to tell exactly how many there are, of very large icy volcanoes. And so they share some similarities to volcanoes on Earth and some differences. But basically what we see are these giant mounds. You could call them mountains, but they're not spiky. They are more softly rounded, but they're at least several miles high.
Mhm.
And they're can be up to 50 or 100 miles across. So they're huge features.
So we're saying they're more like shield volcano-y type than stratovolcano type.
Yeah, that's a great way of thinking about it. They are similar to shield volcanoes in that they are broader and have shallower slopes. However, there is no caldera at the top. So that's one big difference. And they also have this like lumpy stuff. We sometimes call it hummocky. It's not exactly like little hills. They're more interconnected than that. We sometimes call it undulating. Again, this doesn't look like anything else in the solar system. So in a way, we're kind of like coming up with what to call it even. But it's got this lumpy stuff all over the sides. And so like a shield volcano on Earth has smooth sides because there's kind of like thin flows that come out and they're very liquidy and they build it slowly over time. But we don't see either a caldera or anything that looks smooth on these features. So again, there's some similarities and some differences.
So how did you determine these were cryovolcanoes? What's your evidence for that? And also for the audience, and because this is always sort of a conflicting definition, what's the definition of cryovolcano that we're using here?
Yeah, both good questions. So we use a very broad definition of cryovolcano. And when you think about volcanism on Earth, essentially what it involves is material that is mobile and able to move, that's in the subsurface, and it comes up to the surface and it either covers up other structures that were there or builds structures on the surface.
Mm-hmm.
And that's the same thing that's happening on Pluto, we believe. So as I mentioned, we see these crazy tall structures, strange textures on them, and there are almost no impact craters. So impact craters form over time. We see them in other areas of Pluto. We know they had to have formed everywhere on Pluto. So if you find an area that doesn't have them, we know that they had to be erased somehow. And one way to do that is to put new material onto the surface, like a volcanic process.
Mm-hmm.
Another way could be maybe just erosion erases the previous terrain, but that has a really distinctive signature, and we just don't see any signs of erosion. And it's usually you end up with like more like a flat area, right? Crazy lumpy area, for example.
Mm-hmm.
So it's a kind of a combination of we see this young area, we see these really large structures, and they look like they have been built up, kind of like a volcano.
So do we have any idea of, when we say young, I don't want people to think that this is necessarily erupting last week. When we say geologically young, what kind of age are we talking?
Yeah, it's really hard to put an exact date, for example. So we don't have any samples, sadly, of Pluto. But we can place some constraints just based on the rate that impacts should form. And if we don't see any, that gives us kind of a rough estimate. So that age would say something like no older than 1 billion years, which still sounds really old, right? But that's extreme upper limit, and we expect that they're much younger than that. In fact, it's quite possible they have formed in, say, like the last few 100 million years, which still sounds old, I know, but for geology, it's not. And actually, we cannot exclude that this activity has stopped, or we can't conclude that it has stopped. It might still be going. So, although maybe it was not formed last week, we could potentially still have more episodes of this volcanism happening in the future. We don't know that it's completely done.
So I mentioned in sort of my summary that this is telling us that there's more internal heat lasting longer on Pluto than we expected. How is that possible?
Also, something I will freely admit we don't have all the answers on, but we do have some hypotheses of how this could occur. So we know that there's not a lot of ways to produce heat on Pluto, but Pluto is 2/3 rocky material in the interior and then 1/3 icy material on the outside. And that rocky material has radioactive decay occurring, producing heat, just like the rocky material on Earth produces heat. It's just smaller, and so there's less of it. However, if you have some kind of insulating layer, just like if you have an insulating mug, you can hold that heat in. And so you could potentially build that heat up over time rather than just letting it out continually. And I know it might seem kind of ad hoc or, like, why would you think that might be possible? But there's actually other geologic indicators on Pluto that also indicate that maybe there's more heat in the interior than we thought. And so these ideas have come out of just trying to say what is possible. And we know that that could potentially happen. There are ways to form that kind of insulating layer. So that's one idea, is that you could build the heat up over time with an insulating layer. And then maybe you get cracks in the insulating layer and that episodically lets some of the heat out.
I love this. Okay. So what implications does this have for other bodies in our solar system? You said we haven't seen this kind of terrain before. Are there places where we think we should be able to find it, could find it, want to look for it?
That is one of the fun things about cryovolcanism. There are other worlds that have icy surfaces, and there are a few other areas that people have proposed are also cryovolcanic, but they look completely different than what we've seen on Pluto. One example is that I used to say was the best example of cryovolcanism before we got to Pluto is on Neptune's moon Triton. And on Triton, there's these vast, smooth areas that we think were kind of filled in more like a flood volcanic event. That's also sort of similar to how the mare on the dark patches of the moon form. So these are more flood-style events, and you get these vast, smooth plains. So that's completely different than what we see on Pluto. So even though cryovolcanism is probably occurring on other worlds, the conditions on Pluto are just a little bit different. It's really cold, there's a very thin atmosphere, and there could just be a slightly different mix of the ices that is present as well.
So what is next for you with this research? Or next for you just in general with New Horizons?
Great question. So New Horizons is continuing out into the Kuiper Belt. We are currently at about 52 AU, or 52 times the distance from the sun to the Earth. So we are very far out, and we are approaching the edge of the Kuiper Belt. But New Horizons is going to continue to look at Kuiper Belt objects that are somewhat close. It won't be a really close flyby unless we find another target to do that with. And New Horizons is basically an observatory in the outer solar system. So we can look back on our solar system, which you can't do with very many other spacecraft. And so we kind of have a different angle to look at these objects, and that really helps us understand them.
Fabulous. I love this mission. I have loved this mission since it launched. It's one of the reasons I got back into astrophysics. So I'm so excited to see these results coming out, and cryovolcanoes are just awesome. So thank you, Dr. Singer, for joining us. And we hope to have you back again soon to talk more about Pluto and Kuiper Belt objects and cryovolcanoes.
This was really fun. Thanks for having me on to talk about Pluto and New Horizons.
This has been the Daily Space. To all of you watching, this conversation ran longer than we can air here on Now Media. You can catch the rest of the interview in its entirety on our website, dailyspace.org.
While you're there, check out our show notes to find more information on all our stories, including images. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.